Good morning and very warm welcome to all of you. We welcome you all to the physics webinar Stay Home, Enjoy Physics, jointly organized by the Indian Association of Physics Teachers, IAPT RC-7 Gujarat, Essencetech, Department of Science and Technology, Government of Gujarat, and Gujarat Council on Science and Technology GUJCOST. We welcome you all to the second lecture series, Knowing About Atoms, A Journey in Wonderland, by Professor K. N. Joshipura, retired professor, Department of Physics, Sardar Patel University, Vidyanagar. He is also the General Secretary of the Indian Association of Physics Teachers, IAPT. Now I request Professor Dr. Tushar Pandya to introduce our speaker.
Well, good morning, friends. Hello, can you hear me? Can you hear me?
Oh, yes.
Yes. So, good morning, my dear friends and all participants and physics educators. It gives me a great pleasure to introduce Professor K. N. Joshipura, sir. My dear participant, Professor K. N. Joshipura was a professor of physics and head of the physics department of Sardar Patel University. He is retired, but not tired. And he's, yes, he's a very active physics educator and researcher in physics. His field of research is theoretical, atomic, and molecular physics. And dear friends, he has guided about 25 MPhil and PhD students. In this connection, he has visited many countries like USA, UK, Germany, Italy for his research extensions. He has published many research papers in various national and international journals. Dear friends, recently he wrote the monograph of atomic and molecular ionization by electron scattering theory jointly with Professor Nigel Mason, belongs to the University of Kent, UK, and it is published by a Cambridge University Press. At present, he is a General Secretary of Indian Association of Physics Teachers. And dear friends, he is actively involved for over 47 years in educational and outreach activities of the program, which is conducted by a Regional Council of Indian Association of Physics Teachers at all levels. He is a fellow of Gujarat Science Academy and is actively involved in various state level workshops, competitions, teachers awards. And he was also a former honorary secretary, director of the Anand District Community Science Center, where he has conducted many outreach programs of science. Professor Joshipura, sir, is a popular science writer and excellent science communicator and has contributed many articles in scientific magazines, newspapers, and social media blogs. He is an editor and contributor in the annual physics magazine of Pragami Tarang, which is being published by Regional Council of Indian Association of Physics Teachers. And recently he has translated a book on meteoroids, which we say Ulkao, which is written by a famous physicist of PRL, Professor Narendra Bhandari. Well, friends, we have an expert with us. With this brief introduction, I request Professor K. N. Joshipura, sir, for his presentation. Sir, over to you.
Thank you so much. Dhanyavad, Dr. Tushar Bhai Pandya and the friends. It's also a pleasure to acknowledge the Department of Science and Technology. I hope you can see my first slide of the PPT. Is it okay?
Yes.
The first slide of the PPT. So we should thank the Department of Science and Technology, Government of Gujarat, and under this we have the GUJCOST, Gujarat Council on Science and Technology, and the main work is being done by Essencetech. Our youngsters, Harshal Sanghvi, and Harshal Sanghvi is in Ahmedabad, and Chintan Pansasra is in Rajkot. You are all from all over India. I hope you are safe and fine. this is wonderful, wonderful virtual reality. It's a new experience for an old man like me. So it's a very nice occasion. You know, the topic of this lecture, this particular session, is knowing about atoms, a journey in Wonderland. I am thankful to Dr. Tusharbai Pandya for introducing me. Yes, I worked with the Department of Physics at Sardar Patel University, Vallabh which is in central Gujarat. So I am at Anand in central Gujarat. You people are at various places, and this is like a countrywide classroom. You see, in a classroom, the students are not the only student. The teacher is also a student. So it's a wonderful experience. I'm happy to work with IAPT, and I will be now proceeding further. Welcome to this session of the webinar. I will try to sail smoothly with my PPT slides. I don't have what is known as simulation, etc. Hello? It's okay? And others. Yes? Can I proceed? Hello? Can I proceed further?
Yes, sir.
Okay, fine. So this is a talk outline about the atoms. We will start with some ancient thoughts. Yes, the concept of atom, the smallest building block, is as old as our civilization. But they were philosophical ideas. So we'll start with ancient thoughts about the atom. Paramanu, 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 as we call it in our Indian languages. We will go to pre-quantum ideas, the ideas about the atom that emerged from chemistry, study of chemistry, and they were pre-quantum. The quantum was yet to come. And then we will converge to the quantum mechanical atom, various things that we'll get to learn from quantum mechanics. And so this is the outline of the talk. I should acknowledge the credits, picture credits to Google sources. In fact, a lot of literature is also available at the click of your computer laptop. You get so many things, atoms, history, outline. At this stage, I'm reminded of a beautiful BBC film on atoms. In this particular film, there is a small film, you can say, the black and white old film, where you can see our stalwarts like Niels Bohr and others discussing something, and they are having a look at the photographic film of those days. They are looking at the photographic film and trying to understand what's happening. It's a marvelous experience. You can see them. Those people of our ideas, our pictures, our textbooks are there really working. So all such things are available nowadays in Google sources. But still, there is always something special about the interaction, the classroom interaction. Well, friends, if you try to draw about an atom, it looks like this. This is the usual picture, nothing wrong. You know, textbook, you know, school and college studies, when you ask, what does an atom look like? Usually we draw a picture like this. But I want to tell you, and we will elaborate also, I want to tell you that this is an incomplete picture. It is likely to lead to misconceptions. Very briefly at this moment, the atom is not a flat two-dimensional object. It's a spherical object, fluffy object. And there are many specialties, varieties of the atom. We'll talk about this later on, but let us try to avoid the misconceptions. I should thank you. I should thank Chintan and Harshal and others who have been making very important efforts, successful efforts. I thank the organizers and of course participants. Without participants, what is the use of this exercise? In fact, friends, I understand that this is an opportunity given to me. It is like mutual induction. You see, there are primaries and secondaries. I don't know who is the primary and who is the secondary, but there is a wonderful mutual induction. Therefore, it's an opportunity for me. Now, knowing about atoms, what is there? It is a very well-known thing, you will say. And you will tell me, sir, we are quite advanced now. Today we have mobile, computer, ICT, AI. मेरे पास क्या नहीं है? मेरे पास ये है, मेरे पास वो है, लेकिन वो साइंटिस्ट है वो बोलेगा कि मेरे पास है, मेरे पास है. But usually we talk about technology. All these things are there. What not? Dear friends, let me emphasize that technology, all these technologies we have mentioned, are like fruits of a tree. The root is the basic science or basic physics. And the mango session, mango season is going to come. So have a look at the hello, anything? Fine, okay. Have a look at this mango tree. What you see are the fruits. The technology is like a fruit, but there is a root. There are roots. So technology is like a fruit, and the basic science is like the root. From root comes the tree, and then it bears fruit, and we have technologies today in the 21st century. Okay. Now, to give you an outline, friends, the elementary idea of atoms emerged from chemistry. Scientific idea emerged from chemistry. After 1926, the quantum mechanics came up. It gave a clear picture of atomic and molecular structure. We came to know about bonding and structure of solids. Then we learned about semiconductor elements, silicon and germanium. 1948, the first ever transistor was invented, and I'm just trying to give you a look of the bonding in silicon atoms, from where the ideas of the transistors and other devices emerged. Then after 1950, communication, computers, not only gigantic computers, but miniaturization in computers. Then comes the ICT age, the internet, the mobile, the phones, AI, artificial intelligence, robotics. And here is the latest example. Who's this lady? This lady is Vyoma Mitra. Vyoma Mitra is the lady robot of our ISRO, and she is going to Gaganyaan. So from where to where? Such a huge progress. And at the root of, I told you, basic knowledge. दोस्तों, तुम भूल न जाओ उसको, इसलिए सुनो ये कहानी. सुनो, सुनिए, सुनिए, सुनो छोटे से एटम की लंबी कहानी. छोटे से एटम की लंबी कहानी. Friends, wondering about nature is in our nature. At the dawn of civilization, the first ever thought, maybe 5,000 years back, the first ever thought that emerged in Indian and Greek cultures was about the 5 basic elements of our existence. They might be thinking, they might be asking themselves, look at the world around. What do you see? Essentially, what do you see? Earth, that is the hardcore land, that is rocks and mountains and other things. Water, water flowing in rivers, oceans. The other reality was fire, kind of energy, let us say. Then comes wind or air, and finally the sky. So these were the 5 basic elements of our existence. That was the first ever scientific classification of the surrounding. Earth, water, fire, air, and sky. Prithvi, Pani, Agni, Vayu, or Akash. Kind of first ever scientific classification. The idea of the smallest particle, the building block, came almost in the 5th century BCE, and we are reminded of Rishi Kanad. Try to understand the name, Kana, that means the particles, the smallest particle. The Rishi himself was known as Kanada in India, and Democritus in the Greek philosophy. Greek philosopher was the Democritus. They conceived the first idea of the smallest, indivisible, the last ultimate thing. But this was all confined to philosophy. Then comes almost beginning of 19th century, and we have atoms coming to science. The first ever scientific idea around 1803 came from the chemist John Dalton in the UK, England. He postulated the existence of atoms, tiny, invisible, indivisible, final building blocks of all matter. And he was required to make this assumption in order to explain chemical reactions. It started with chemistry. Physics was yet to enter into this arena of atoms. Soon after, it was Emilio Avogadro in Italy who gave the concept of molecule as distinct from atoms. And that was around 1811. In our Indian languages, the atom is paramanu and the molecule is anu. So then the idea emerged in chemistry essentially that we have simplest chemical substances known as chemical elements. They are made up of identical atoms. Atoms are the building blocks of chemical element. And chemical compounds, another kind of substances, a little more complex substances, compounds are made up of identical molecules. And the idea is that the atoms form molecules. So physical building blocks are molecules, chemical building blocks are atoms. This kind of idea started emerging in 19th century. Atom was still a kind of hypothesis. And physicists, on the other hand, of those days, were more engaged in experiments and theories on directly observable phenomena. Directly observable. The atom was not observable as such. But I would like to mention that from Faraday's experiments, there were some early hints pointing out at electricity or electric charges as constituents of matter. There could be some charges within the atom, maybe, who knows, perhaps. This was a kind of hidden thinking that was going on. But in the meantime, excitements were mounting up in chemistry. Here comes an important development. 1869, Mendeleev in Russia saw a great order in the grand design of nature, order out of just random collection. Of course, there were some early ideas also. I want to tell you about the periodic table of elements that was formally put up by Mendeleev, and that was around 1869. When we return to this in physics, we will call it periodic table of atoms, periodic table of elements, chemistry, periodic table of atoms, physical ideas, how the things are arranged, what is the scheme of the things, we will call it periodic table of atoms. We'll return to this, but meanwhile, let me tell you, the path of knowledge on atoms was lit up by light, you know. I mean, there was an important position of light in the study of physics. In those days, 19th century, varieties of optical phenomena were studied, and you are familiar with this, starting from reflection to diffraction to interference, polarization, diffraction also. These were being studied by various physicists. Light was the center of attention. And who is this man? This is James Clerk Maxwell, who conceived a great idea of unification. And that was electromagnetic wave theory of Maxwell in 1864. All these things have led gradually to the development of physics and knowledge about atoms. Maxwell's theory was a kind of unity in diversity, unity of all various kinds of light radiation into from the diversity. So kind of unity from diversity. That was Maxwell's idea. Meanwhile, another development, since the days of Fraunhofer, almost 1814, there was a keen interest in the spectra, spectral lines emitted by different sources of light. Now, today, spectroscopy is a tool of not only theoretical research, but also experimental research and development and application in various walks of science and technology today. So you might be thinking from this page, you might be thinking, oh, these are like different topics in our different papers or courses in our BSc level physics. You are talking about light and then electromagnetism and then spectroscopy. At the first sight, it looks like different, but the developments have been quite coherent. Meanwhile, let me point out at some other development. There was a parallel development about the kinetic theory. It started almost 1738, where atoms and molecules were required to be assumed. They were assumed as invisibly small and extremely large particles, extremely large in number, always in motion. And this kind of a model, the ideal gas model, was required to explain the properties of gases. For example, how is it that a gas exerts pressure? The interpretation depended on tiny atoms and molecules. They are exerting forces by collisions with the walls, etc. And this kind of a development also was important. This man is Boltzmann. This man is Boltzmann. Gradually, the whole idea of classical statistics or statistical mechanics came up, and that was known as Maxwell-Boltzmann statistics. Apart from Maxwell, Boltzmann himself was a staunch believer in atoms. Although there were some apprehensions, there were some people who did not believe in atom as reality. I am reminded of some name like Oswald. They even tried to disappoint, they even tried to laugh. Really, there was some controversy. They tried to laugh at the Boltzmann. You are talking about something which does not exist really. It looks like hypothesis. Boltzmann was disappointed with this criticism, and the story is that he committed suicide in 1906. That was about Boltzmann. But now, friends, let us return to spectroscopy. And we imagine a scenario towards 19th century. We are proceeding in history along the timeline. Imagine a scenario. The scenario is that a spectroscopist Angstrom, if you are familiar with the name, Angstrom was a spectroscopist. He meets Balmer. Now, Johannes Balmer was a school teacher. He was a mathematics teacher. I don't know how they met. So we have to just imagine some kind of a scenario. An experimental physicist meets a mathematician, and he shows his experimental data on the spectral lines of elemental hydrogen spectra, which are very known. Very well known. I'll show it here. See, what you see is a series. There are 4 members, prominent members. What you see is a series of thick lines. Actually, they don't appear to be so thick, but to make it clearly visible, this kind of a picture has been developed. The names are H alpha, H beta, H gamma, H delta lines. They are spectral lines of element hydrogen. This was obtained experimentally by people like Angstrom, Lummer, Prangshem, and others. And their wavelengths were also measured. You can see the wavelengths written over there in nanometers. This data was shown to Balmer. So we have to imagine that they met somehow. I don't know why or how. Balmer, mathematician, looks at the wavelengths, lambda. For example, the first wavelength is 656.3 in nanometers, and in angstroms it is 6563 in angstrom. He was a mathematician. He got some idea. He got an idea to arrange all these numbers of the that means wavelengths of the spectral lines in terms of a mathematical formula. He started with 1 upon lambda, and he was able to arrange the numbers in such a way that the equation 1 comes up, Balmer's formula. In this formula, I mean, he was able to get it somehow. In this formula, R is a constant. Later on, it was known as the Rydberg constant. N is an integer. Wonderful thing. Wonderful. N is an integer. It starts with 3. If you write n equal to 3, you get H alpha line. So it starts with 3, 4, 5, 6. But this is an empirical formula. Experimental values are fitted to this formula. Fitting formula, you can call it. But it correctly predicted the wavelengths of all the lines. That was the success. Empirical formula fitting into experimental observation. Why does the elemental hydrogen emit only certain lines like this? Why are the wavelengths ordered as per the mathematical formula of Balmer? Nobody knew. In 1897, just when the 20th century was about to knock at the door of the world, J.J. Thomson in England made a fundamental discovery. He tried to study the electron beam using electric and magnetic fields. He was able to find the charge to mass ratio. And he was so confident that he made a statement. There is no escape from the conclusion that they are charges of negative electricity carried by particles of matter. So electron is recognized now as a fundamental particle of matter. But how is it arranged? Where is it actually? Basically, matter is electrically neutral. I mean, when we touch normally other objects, we don't feel a shock. The matter is electrically neutral. So the ultimate particle, that is the atom, must also be neutral. And therefore, Thomson thought, along with electrons, there must be positive charge also. So the atom becomes a system with some internal structure. Thomson had his own ideas about the structure. But another development also took place. Friends, we have entered 20th century. Let us have a look at the physics up to the year of 1900. Let us have a look. All this physics before 1900 is known as classical physics. What are the contents? What are the main branches of classical physics? You know, just to give you a quick highlight. Basically, it is the classical mechanics. You know, mechanics plays a fundamental role in physics. Ultimately, you're trying to explain how the things are moving, motion of objects, bodies, particles, classical mechanics. The next part is optics, various phenomena of light, and then extended to other radiation also. There is a branch known as heat, thermodynamics, statistical mechanics, and electromagnetism, electrodynamics. These are the essential contents of classical physics. If I'm missing something, I should simply say, etc. So this is the picture of classical mechanics. It's a body of knowledge based on our experience, experiments, and hypothesis, theory, and so on. And there were some people who were more or less satisfied with these ideas. Towards the end of the 19th century, somebody also made a remark that there is hardly anything new to be known. See, the physics appears to be perfect with all these ideas. Maybe you can go for more accurate measurements and things like that, but that was not to be. There was a lot of things. There was something very interesting that was revealed. Now, story of the atom enters 20th century. We are in the story, we are in the 20th century. Physically, we are in the 21st century. Okay. So, a very important period, 1900 to 1913. It was a historic period of developments in physics. And I'm reminded of this book, 30 Years That Shook Physics. In fact, this particular name was given, we came to know about this book from none other than Professor S.P. Pandya, Sudhir B. Pandya, who was my Gurunam Guru. I remember him. He told us about 30 years that shook physics. The book was written by George Gamow, and it was an excellent account of the developments in physics. 30 years that shook physics. Shook physics, indeed. A lot of changes were made. Have a look at these two giant personalities of those years. You have Planck discussing something with Einstein, as something is there, as if they are exchanging quanta of something. Planck and Einstein put forward the quantum theory of radiation. Photon as a particle of light, corpuscle of energy. The energy was given as E equal to h nu, where h is the fundamental constant, Planck's constant. Meanwhile, Thomson was thinking of giving some idea about the structure of the atom. He gave a model of the atom in which the positive charge was smeared out in the entire positive charge of the atom. There were some particles like electrons. Probably if you see the watermelon, tarbuj in Gujarati, kharbuja, if you see the watermelon, it can give you some idea of the model of the atom that was given by Thomson's model. It was some kind of an attempt, let us say, at this stage. Meanwhile, in 1911, Rutherford carried out alpha scattering experiment. Probably he was interested in knowing how the positive charge is arranged within the atom. And he carried out the experiments with thin foils of gold. What is the result of the experiment? The atom gets the nucleus, central, massive, positively charged core. So now the atom is becoming a system with positive and negative charges, and the positive charge is in the concentrated hard core. That is the nucleus. This is about Rutherford. And the picture is there are the negatively charged electrons revolving around the positively charged, extremely tiny nucleus. Probably he had an idea of the planets revolving around the sun. And this is like miniature model of the planet, Rutherford's model. But my dear friends, electrons revolving around the nucleus invited trouble from classical mechanics, electrodynamics, let us say. The point is that the circulating electron is an accelerated charge, circular motion, and it would emit radiation. It would spiral down to the nucleus in no time. Such an atom won't be stable. Oh, that's a great difficulty. Our atomic wonderland would collapse into nothing. We won't be there. I won't be there, you won't be there. What will happen? What will happen? It's a great surprise, great confusion also. But meanwhile, a young man was also coming up. You know, this is like a game like cricket where a youngster comes up and starts hitting. Hitting is like putting people into surprise and wonder. There were some questions, confusion also prevailing. In this situation came up Niels Bohr. He enters the arena and gives a model based on certain atom. It is here that quantum meets atom. What were the questions prevailing in the mind of Niels Bohr, let us say? The first question was about the stability of the atom. You know, classical physics says that such an atom with electrons revolving around the nucleus won't be stable. This was one of the two questions. The other question was about the emission or absorption of light, the line spectra. The Balmer formula was okay, it was a formula, empirical formula. How to explain the emission of certain lines, say in hydrogen? Bohr concentrated essentially on hydrogen, the simplest system. These were the two questions, and Bohr stepped out. Bohr stepped out and made bold postulates. He thought, you see, in order to proceed further now, I have to make some assumption. Later on, maybe some interpretation will come up, but Bohr says, I want to assume postulate of stationary state, the first postulate. Bohr says atomic electron stays normally in one of the stable non-radiating states. In that way, it defies classical physics. Maybe he says this is an unknown system. Why do you assume that it will also follow the rules of classical physics? Let me assume stationary states. First assumption or first postulate. The second postulate is frequency postulate. The question is about the emission of light, energy. This postulate second says the electron in the atom emits or absorbs light only through a jump from one state, say N, to another, M. So then Bohr put forward an idea of certain initial state with energy En, final state, discrete state with energy Em, and the difference of energy, when the jump takes place, the difference of energy is in the form of H nu Nm. Nu Nm is the frequency of radiation. You will understand that there is either emission of radiation or absorption of radiation. These were the postulates made by Bohr to explain the line spectra of the hydrogen atom. But they turned out to be revolutionary ideas. How revolutionary? Because it is for the first time that the quantization enters the realm of matter. Till about 1913 or so, quantization of radiation was getting a clear picture. It was getting the acceptance. Radiation behaves like a stream of energetic particles of energy, photons. But this kind of quantization of energy has appeared for the first time in the form of Bohr's model. And then the concept of discrete stationary states of electrons in the atom, total energy is quantized. Therefore, total angular momentum of the electron in the atom is quantized. And here comes an integer n, mvr equal to nh upon 2 pi, h by 2 pi is called h cut. And this quantization is characterized by a number, an integer called the quantum number, n equal to 1, 2, 3, 4, 5, 6. Let us recall Balmer's formula. In Balmer's formula, we had an integer, n equal to 3, 4, 5, 6. There was no meaning. It was just an integer of the formula, mathematical formula. Now this n in Balmer's formula is essentially n equal to 3 or 4 or 5. And that is the quantum number describing the state. So n equal to 1 is the ground state of the electron. 2, the first excited state. 3, n equal to 3, the second excited state. And the jumps, say for example, from 3 to 2 gives rise to the first line, H alpha line. This was the theoretical explanation of H alpha, H beta, H gamma lines. And the success of Bohr's theory is that it correctly reproduces the wavelengths of the spectral lines. So there was a big change, big revolution. But the idea of discrete states in the atom, non-radiating, discrete, stable states or orbits, we may call it, and the idea of quantum jumps was hypothetical. Some people ask, is it reality or just a theoretical artifact, theoretical device? Since we want to understand the spectra, we make a device, theoretical device, let us say. Some people thought if this is a reality, then the atomic excitation and emission can be initiated by some other radiation or by some other means. For example, you can bombard an atom with electrons. The electrons would transfer appropriate amount of energy to the atom, and in turn the atom would re-radiate that energy. We could see this. We could see the loss of energy of the electron, and that would be another evidence of Bohr's ideas. With this 1914, Frankfurt's experiment was performed, It was essentially electron energy loss experiment in today's world, today's jargon. Frank Hertz's experiment was electron energy loss experiment, and it was an evidence of essential ideas of quantization. The results were expected theoretically, and they were confirmed by Frank Hertz's experiment. This was done on mercury atoms, mercury vapor in a discharge tube. You can have a look at the details. The results were obtained and interpreted in terms of the inelastic collision of electrons on mercury atom, and that confirmed discrete energy levels. Yes, Frank Hertz's experiment, 1940. Friends, I want to tell you, I want to add here that Frank Hertz's experimental kit is available nowadays, and you don't have to use mercury. They are using some others, other gases perhaps, but you can have a look at it. In fact, our laboratories can have this as a very important experiment. Okay, so some evidence, some support, but still confusion continues. This is only about the hydrogen atom, the one electron atom, the simplest atom. Good, we got a good picture. But many electron atoms posed many problems. Larger the electrons, more and more the problems. And the efforts were not successful. We will not describe the intermediate efforts, but they did not lead to successful results, explanation of experiments. New experiments were coming up. New observations were coming up. But the theory seemed to be a little bogged down. Theory was looking for a giant quantum leap. As if there was morning twilight, there was some semblance of sunrise, but the sun was about to rise, not yet above the horizon, let us say. A sudden turn comes in the story of the atom. There was a young man, de Broglie. He came up with a question. Can an electron behave as a wave also? We have been talking about the electron as a particle of mass m and charge E and ratio E by m, and it is deflected by electric fields, magnetic fields. You form a beam of electrons. Okay. All the time we are talking about the electron as a particle, maybe tiny particle. De Broglie asked a question, can it not be a wave? So then comes the concept of matter waves, the de Broglie wavelength, and we have the famous formula for de Broglie wavelength, lambda dB, let us say, h by p. P is the momentum of the particle. Okay. Another development, an epoch-making idea, Heisenberg's uncertainty principle. All classical physics that at least in principle, at least theoretically speaking, the measurement of any physical quantity must be exact. I mean, there is no reason except for experimental uncertainties or statistical ideas. There is nothing like uncertainty in classical physics. Now, uncertainty assumes the form of a principle. So, I mean, this is another blow to the ideas of classical physics. Then comes Schrodinger. If the electron is not just a particle and if it is a wave, then it must also have a wave equation. You see, wave equation for waves is known in classical physics. We have studied in our UG classes. Now Schrodinger is talking about wave equation for electron as a wave, matter wave. And it comes up with the Schrodinger equation. Symbolically, we write this H as H psi equal to E psi. H, we tell you about this. Psi, psi is the source of knowledge. Psi is a function. It's a solution of the Schrodinger equation. In general, it is a function of space coordinates and time. We talk about general time-dependent situation. H is the Hamiltonian operator. Now with this psi comes another idea. Probability comes into physics in a new form. We had probability in the form of statistical mechanics, but now comes probability for an individual particle also, the electron. It is such that the absolute psi square gives the position probability density. You think of a unit volume around position R, it shows psi square absolute shows the probability of finding particle in a unit volume around the position R, defined by XYZ. Okay. Now, friends, I hope you are listening to me. Perhaps in a kind of anxiety, you will say, we want to know about atoms. Our topic is on atoms. And you are talking about quantum mechanics. Why quantum mechanics here? Why quantum mechanics? True. And this looks like a question in anxiety. But friends, quantum mechanics is the gateway to atomic and molecular knowledge. And it begins with the Schrodinger equation. That is the stepping stone. So in this picture, a cloud, a haze, something like not something like a clarity. In a haze comes the Schrodinger equation, a rather picturesque way of saying that it is something unusual. Cloud, because of many things, because of our lack of clarity, lack of clear understanding, and because of the inherent probability idea, inherent uncertainty. But it begins, as I said, with the Schrodinger equation. Let us write, I mean, no use talking about Schrodinger equation. What we wrote down was only symbolic equation, H psi equal to E psi. Let us write down three-dimensional Schrodinger equation for a particle of mass m. Let us talk about non-relativistic situation. And we say that the particle is moving in a field of potential energy VR. Potential energy function, V is the function of R. We are discussing stationary, time-independent situation. And here is the Schrodinger equation. We can't avoid it at this moment. Some ideas are required. Please get a clear-cut idea of various terms in this equation. You see on the left-hand side, we have a square bracket. The square bracket shows the Hamiltonian operator. You may ask later on, what is an operator? What does it do? What does it give you? But in brief, I mean, we have to cover a long way. So in brief, the first term is the kinetic energy operator. The second term is the potential energy operator. The square bracket is the Hamiltonian operator. It operates on the psi. Psi is parametrically dependent on E, total energy of the system. And this is the detailed version of H psi equal to E psi. E is the total energy, that is the sum of kinetic energy and potential of the particle or the system. What do you know if you know psi? We have given an answer: probability density, position probability density, plus other things will also be obtained. But I want to give you a slightly different picture. Oh, in between, this looks like a conference of eminent physicists, the leading physicists of those days. This picture was drawn by one of my students almost 20 years back. You imagine that people are sitting and chatting. They are in fact playing a game. You have Einstein, Schrodinger, Bohr, Planck, de Broglie, and here's Heisenberg. What are they doing? They are playing cards. Oh, I thought they may not play. Einstein had said, God does not play dice. So we should not also play dice, but they can play cards. Why cards? Because playing cards involves some kind of uncertainty or probability. So to highlight that idea, we imagine all these people playing cards. And what are the cards? You can see psi and phi, and maybe they are discussing. Friends, this picture is also meant to highlight an important debate that went on between Einstein on one side and Niels Bohr on the other side. Einstein was not in favor of kind of inherent uncertainty at the microscopic level in the atom or in the electron in the atom. And so Einstein said, God does not play dice. It does not hide things. Bohr said, it is not our business to tell God what to play and what not. So this is the idea behind just this kind of a picture. Just to give you some idea, a funny way of putting up the thing, okay? What started with a wave equation for a particle, the Schrodinger wave equation, evolved eventually into a strong knowledge based on a foundation. And the foundation was in the form of fundamental postulates of quantum mechanics. What are postulates of quantum mechanics? Well, in a lighter tone, you can compare postulates with the rules of a game. Rules of a game. We start with the rules of quantum mechanical game, arrive at all the important deductions, but it is now a very well established knowledge, quantum mechanics. All right. Schrodinger equation is basically a second order linear differential equation. The solution is psi. I'm reminded of a beautiful explanation of the Schrodinger equation given by Halliday and Resnick book, 4th edition, volume 2 extended, and I have it. Look at this, very nice way of putting the thing, excellent way. Have a look. The Schrodinger equation is like a machine. It's like a machine. Oh, really? Ah, yes. Imagine a machine. I mean, talking about the Schrodinger equation. So Schrodinger equation as a machine. See, in a machine, what is there? There is some input. Then churning, processing. You know, in our roadside sugarcane juice machines, there is an input, processing, output. Similarly, in a machine like this, there is some input, there is processing or running, let us say solving the Schrodinger equation, and there are outputs. Beautiful way. This is given in Halliday-Resnick. What is the input in the Schrodinger equation? You said the input is the potential energy function. What is the system that you are talking about? Potential energy function. For example, yesterday Dr. Tusharbai Pandya talked about the harmonic oscillator. You can set up a one-dimensional harmonic oscillator problem with appropriate potential energy function. Apart from the potential energy function, you need the boundary conditions, the second order differential equation. You need boundary conditions, 2 boundary conditions. So these are the inputs. With these inputs, you are trying to solve the Schrodinger equation. For some cases, a few cases only, exact mathematical solution is possible. So the next step is to running the machine or solving the Schrodinger equation. Friends, today we have a lot of advancement, a lot of things have been made possible by computers. Computers have been solving the Schrodinger equations for complex systems. So you may call this essentially a computer nowadays. Okay, when you run or when you solve the Schrodinger equation, maybe exactly in some cases, approximately, but accurately, very accurately in many other cases, you get the outputs. What are the outputs? Solution of the Schrodinger equation, the wave function. Solution gives you quantum numbers. We will mention about them. One is of course mentioned already, and the integer. It gives you energy levels and many other things, a lot of information. The output is in fact the whole knowledge about atoms. So I thought this is a very good analogy, some kind of picturesque way of putting the things. With this, what do we get when we solve the Schrodinger equation? As I told you, the wave function of the electrons, well, in the beginning, we may talk about one electron system, fine. You have an exact solution, the famous hydrogen atom problem. We have done it in our quantum mechanics courses. But when you talk about many electron atoms, the systems are complicated. but somehow approximately and accurately. We get the wave function of electrons in the atom. We get the total energy of the system, as I told you. We get quantum numbers describing the states of the system. Please note, my dear friends, that the total energy of the electrons in the atom is negative. Total energy is negative, indicating bound states. For hydrogen atom, the total energy is equal to minus 13.6 eV. See the negative sign. What does it mean? It means that if you are able to supply at least 13.6 eV, the total energy will become zero. The proton and the electron of the hydrogen atom will become free. Conversely, a free proton and a free electron almost at zero energy. Come closer, they will form a bound system, and in the process, an ultraviolet photon of energy 13.6 eV would be emitted. Bohr's theory, as I told you earlier, agreed with measurements. The quantum mechanics of hydrogen atom also reproduces the same thing. This value given by theory agrees with the measurements, and we said that the ionization energy of hydrogen atom is 13.6 eV. In experimental jargon, they call it ionization potential, but in theory, we will call it ionization energy. This is a very well-known number, 13.6 eV. Another important information, and that is about the size of an atom. Size of an atom, average radius. This is what you get from the quantum mechanical derivation. You derive it, starting with the wave function. For hydrogen atom, there is a definition of average quantum mechanical values of dynamical variables, observables. So, for hydrogen atom, the Bohr radius A0 turns out to be the most probable radius. See, now you are in quantum mechanics. A0 is the most probable radius. The average, that is the quantum mechanical average radius, is 3A0 by 2, 3 by 2 of A0. And this value is 1.5, 10 to minus 10 meter. And here is an interesting question. How many hydrogen atoms can be lined up? Please see the mistake. How many hydrogen atoms can be lined up side by side in 1 nanometer length? See, what you have is 10 to minus 10. What you want is nanometer length, 10 to minus 9. So this will become 0.15. If you work out, you will find that almost 7 atoms can be arranged side by side in 1 nanometer length. Of course, this is a very simple picture. We are just ignoring interactions in the atoms and so on, just to give you an idea of the size of an atom. The size or the average radius of the hydrogen atom is 1.5 times A0, or in meters, it is given here. Fine. This is the information that we get. Now, talk about many electron atoms. So, the question is, how are the electrons arranged in the atom? They are not crowded up. No crowding. These days also, we should avoid crowding, social distancing, keeping safe, etc. They also keep social distancing, electrons in the atom. And here comes a very important property, fundamental property, the spin property and the Pauli exclusion principle. Have a look at this historic picture. Niels Bohr and Wolfgang Pauli, they are looking at a spinning top. So always the idea comes from some realistic experience. Maybe somebody got the idea of the spinning of the electron from spinning of a top, or even rotation of the earth, who knows. But the idea has worked. The idea was given empirically by 2 young people, Govt and Uhlenbeck. The idea was taken up by Pauli, and he introduced another quantum number to understand spin quantum number to understand the arrangement of atoms, arrangement of electrons in the atoms. So finally, at the end of all this, the set of quantum numbers, the 4 quantum numbers, N, L, ML, and one more, MS, defines the state of the electron in an atom, many electron atom. These are the key quantum numbers, 4 quantum numbers. Some details I would like to give, not much, but some ideas. Principal quantum number N indicates quantization of energy. N can take up values like 1, 2, 3, 4, etc. And we say that these define, N defines shell. Shell, you know, like a citadel. Killa ban jata hai, strong shell. That's the idea. That's why the word shell has been used. K shell means N equal to 1. L shell N equal to 2, and so on. Within the shell, we describe another quantum number, the orbital angular momentum quantum number. It shows the quantization of angular momentum. It is L, it starts with 0, 1, 2, 3, 4, 5, goes up to this, N minus 1. And there have been symbols to indicate each of these values. For example, L equal to 0 shows S. The next is P, DF. This is strange. For a spectroscopist, the alphabet is not A, B, C, D. It is S, P, D, F, G, and J. Wonderful, wonderful. There is a reason also why these symbols have been adopted. The next is projection quantum number. It shows the quantization of the Z component of angular momentum. We call it ML, but there is likely to be some confusion because M we have used for the mass of the electron. If you can avoid the confusion, fine. Otherwise, write ML. ML can go from minus L to plus L, including 0 in steps of 1. So there are 2L plus 1 values. And additionally, we have to define the spin projection quantum number with reference to an external z-axis plus half or minus half. So this describes the atom in terms of quantum numbers. In the atomic wonderland, electrons accommodate themselves in order of increasing energy starting from n equal to 1. Essentially, the electrons are all identical fermions. They follow Pauli exclusion principle and they maintain separation. Okay, fine. Now, we come back to that question we posed in the very beginning. How does the atom look like? The common picture is, of course, here. We show the nucleus, which contains protons and neutrons, and the nucleus is surrounded by electrons revolving, say, in circular orbits. Of course, the idea of orbits is no more valid. It's not very accurate. I want to point out that there could be several misconceptions here. We should know. We should know. We may draw a simple picture, but let us know, first of all, that an atom is not a flat two-dimensional object. We have drawn it on a piece of paper, maybe some projection, but it is not a flat two-dimensional object like this. The atoms are spherical. And they are fluffy objects, cloudy objects. If they happen to travel in the atom, I don't know how would it look like. There will be clouds and then void and then clouds and then void, and finally I can see distant point cloud sharp object. I don't know what will happen, so I have to return back. Something like this, something like this. The atoms are essentially fluffy objects. Next, on this scale, the nucleus would be just invisibly small. But then we have to show something. So approximately, we have shown this. And the final point, orbits, the trajectory or path of the electrons is not sharply defined. Not sharply defined. But with this background, we may continue with the simple picture of the atom. Okay. Now, with this background, we may look at the varieties of the atomic wonderland. Now we talk about periodic table of atoms. And that is well known, that is well known. The periodic table of atoms. You see the atoms, that means chemical elements, arranged in columns, in rows also. Start with the hydrogen atom. It is an exactly solvable problem. Within the framework of quantum mechanics, it is exactly solvable. We have discussed something about this. And if you want to place the helium atom, the next one, oh, it should be here. That is the proper place. We say that hydrogen is Z equal to 1, the atomic number Z is 1, the number of protons. Helium is Z equal to 2. In going from hydrogen atom to helium atom, several things change. For example, instead of 1 electron atom, now you have 2 electron atom, the helium atom. Both the electrons in the helium atom are attracted by the nucleus. They mutually repel. They have to follow the Pauli exclusion principle. And if you say that for 1 electron, the coordinates are x, y, z, r1 equal to x, r1 as x1, y1, z1, r2 as x2, y2, z2. So many coordinates are involved. Therefore, the Schrodinger equation becomes a complicated differential equation of many variables. The exact solution is not possible, but rigorous, accurate solution has been made possible. The important thing to realize that in the helium atom, the 2 electrons are quite satisfied. They are content. They are in the K shell, 1s we call it. They have the opposite spin and they find very comfortable. This is our beautiful home and they are so happy that they are tightly bound. And it's a K shell, very strong shell, helium atom. Friends, we will not describe the whole thing. It will take a lot of time, you know, but just try to go from helium, Z equal to 2, to lithium, Z equal to 3, just one more electron outside the K shell. You see the third electron has to go out. Pauli exclusion principle, distancing, let us say, social distancing. Okay, so the third electron, let us say, in the lithium atom, it is outside the closed core of 2 electrons in 1s. So the last electron, you call it odd electron or unpaired electron, will see the screened Coulomb potential of the nucleus. So it is rather loosely bound. See, just a question of one more electron from helium to lithium. Helium most tightly bound, lithium very loosely bound. And then other descriptions. In a way, in the periodic table, the naturally occurring element, the last naturally occurring element is uranium with Z equal to 92. Okay, friends, there is one more thing which we should mention, and that is about atoms of the same chemical element occurring in different varieties. They are isotopes. Here you cannot see the isotopes. You may mention, for example, that hydrogen has 3 isotopes: ordinary hydrogen, deuterium, tritium, but they are essentially hydrogen atoms. And all elements, all atoms in the periodic table have their own isotopic varieties. This is one of the wonders of the Wonderland, atomic Wonderland. Wonderful. Okay. As I told you, friends, the strongest atom is helium, the first ionization energy, the energy, minimum energy required to remove the single electron, 1 electron from helium atom. First ionization energy is 24.6 eV. And that is the smallest atom, compact, small. On the other hand, you think of atoms like lithium, sodium, potassium, alkali atoms. They have an extra electron, odd electron outside the closed core. So the largest atom in terms of the average radius is cesium, largest in terms of size I am talking. And further, I'll simply mention that depending on the electronic structure The atom can have electric properties. The atom can have some sort of a field around it. And this will determine how the atoms interact with each other. We have inert gas atoms. We have very active, reactive atoms, and so on. That's how they build up molecules or solids and so on. That is the beauty. All things are made up of atoms. Now I am going to make a statement about atoms that was made by none other than Richard Feynman. What does he say? All things are made up of atoms, little particles that move around in perpetual motion, attracting when at a little distance apart, repelling when being squeezed into one another. In this one sentence, there is an enormous amount of information about the world. A great amount of wonder is now contained in this sentence, and this was given by Richard Feynman. Little particles, all things are made up of atoms, so the fundamental little particles, they move around in perpetual motion. Depending on the temperature, they have kinetic energy, they are moving around. And as I told you just now, the atoms usually attract each other when at a reasonable distance. If they are far apart, of course, they won't attract, and there won't be any interaction. At a reasonably small distance, they try to attract each other. But if you try to bring them closer, try to squeeze them, then there is a no, then they will repel. It is at a distance where the electronic charge clouds begin to overlap, and then there is a no, stay away from me. Atoms will repel at small distances. This is the characteristic of interatomic forces. And as has been rightly said, in this one sentence, there is an enormous amount of information about the world. Who said this? He's telling us in a typical fashion. This was Richard Feynman, one of the best teachers of physics. We are all familiar with Feynman's lectures and other books. Surely you are joking, Mr. Feynman, etc., etc. But I thought this was a very important statement made by Feynman about atoms. Fine. We are now converging to the end of the lecture. Atoms are mostly, they don't like to be aloof. They don't like to stay alone. Of course, there are exceptions like inert gases, where they are monoatomic gases, but exceptions are there. Atoms mostly do not like to stay alone. They form molecules. Another wonder of the atoms. And the most important molecules are O2 for us, H2O, water. Water is the molecule of life. There's a separate wonder of the molecular systems. We may not talk about this, but the atoms form molecules usually. So atoms and molecules together form solids, liquids, gases, plasma. And the whole world unfolds now. The whole surrounding unfolds. Atoms, molecules, giant molecules like protein, amino acids, even virus, biological cells, bacteria, larger organisms, complex life, plants, animals, human beings, civilizations, nations of the world, the earth. Oh, what a journey. And this is not enough. This is not enough. From macroscopic objects of our surroundings, we talk about planet Earth. Planet Earth, Prithvi. Yatra Vishwam Bhautyek Needam. I am reminded of Vedas. They say the whole world is like a nest of birds. All birds are staying here, happily contented, cooperating with each other, not fighting. So on planet Earth, we have Yatra Vishwam Bhautyek Needam. And as you go out, you see solar system, stars, galaxies, and the whole universe. Wonderful. This is a wonderful journey. Friends, we entered the wonderland of atom. and reached out to span the whole universe. ये कहाँ आ गए हम, हैं? ये कहाँ आ गए हम यूं ही साथ चलते चलते. That was the story of the atoms. Please excuse me for missing many things in this outline. I think I should stop here and invite some discussion. तो ये थी छोटे से एटम की लंबी कहानी. सुनी आपने छोटे से एटम की लंबी कहानी. I am sure, I hope it will raise more curiosity, more questions. And just one point that I want to make out here is about an article that appeared in Resonance magazine of Bangalore, Indian Academy of Sciences. My article appeared in 2013. It was about the size of the atoms, how small and how big it is there. Interested can refer to that. So with this, thank you so much. Dhanyavad. I will stop my discussion, my lecture, and over to you, Harshal. What do we do next? Thank you. Hello.
Yes, thank you so much, sir.
Okay, very nice.
Now
Hello.
we are taking questions from the participants and
Very nice.
faculty.
They are still wondering.
Joshipura, sir, just a minute. Yes, any questions?
Hello.
Yes,
Sir,
yes.
Can you stop sharing the screen?
Okay. Stop sharing. Where is that stop sharing?
Sir, in the middle of the
Stop
screen
meet.
on the top. Yes, not stop meet, stop sharing the screen. You would have an option.
Pause share. Pause is there. Is it okay?
Stop share.
Does it work? Stop option is not there.
Okay.
Pause share is there. Now it has come. Okay.
Yes, perfect.
Right. Please. Oh, yes.
Yes, so whoever wants to ask the question may just raise their thumb so that we can take their question. Yes, there is one student.
I can see some question. What is the shape of an electron? Very nice. What do I say? I say that the question is not relevant because the electron is not like a day-to-day object. And the interesting thing is that the electron doesn't have an internal structure also. So it is just like a point object, and point is spherical. If you want to satisfy yourself, you say that the electron is just a point or shape. But when we talk about the shape of the electron, we have in mind our macroscopic objects like squares or cubes, etc. So I hope I will be able to, I'm able to satisfy you, not much, but to some extent. Yes, please.
Yes, sir, we have one more question from a
Please.
student. His name is Nisarg Vyas.
Please.
Sir, am I audible?
Yes.
Thank you very much, sir, for this amazing informative session. Thank you very much, sir. Thank you very much. Sir, can I speak in Hindi, sir, if not a problem?
Hello. Hello.
Hello. Can I speak in Hindi if not a problem? I am not comfortable in English. So, sir,
no problem.
सर आपके क्वेश्चन आपके लेक्चर के बाद जो मुझे लग रहा था कि मुझे समझ में आया है वो समझ में आया कि अब नहीं समझ में आया है.
Several questions.
So first question, sir, I have got 2-3 questions, but I'll ask only one for the moment. First question is, बोहर ने अपना first postulate रखा When
Yes,
I suppose
please.
there is some network problem with this audio.
Okay. Meanwhile, friends. Hello. I can read a question. Oh, the question is about those numbers. I mean, the letter symbols. L equal to 0 is S. L equal to 1 is P. So L, quantum number L equal to 0, 1, 2, 3 has symbols S, P, D, F. And it is not like ABCD. The reason for SPDF is the first letter of series of spectral lines, like sharp for S, P principal, D diffuse, F fundamental. And then they thought, let's go back to our usual alphabet. So this is the historic way of labeling the numbers by their symbols. I could see. Aha. Another, can I read the question and answer? Hello?
Yes. Yes, sir.
One of the questions I read is, what is spin? Macroscopically, we think in terms of day-to-day objects. We see the top as spinning. We have the Earth and planets also spinning. So at first sight, it looks as if the spin is like spinning around some axis. And we try to draw the classical ideas. Let me try to tell you very briefly that the spin is an intrinsic property. Just as the electron has mass, it has existence, it has charge, it has spin. If you add something more, you can say that the spin is the consequence of the theory of relativity. But the grand scheme, the grand design of the nature is such that there are particles with spin half, the electrons, protons, neutrons. There are particles with spin integers, 0, 1, 2, 3. I mean, this is how the nature has done it. If I can answer how it has happened or why it is happening, I would be very happy. Maybe in future we'll come to know about it. But at the moment, what I understand is that we have interpreted this nature, the grand design of nature, by saying that the spin of the fundamental property, spin of the particles can be either half integral or it can be integral 0, 1, 2, 3, 4. Accordingly, we have two kinds of particles, the fermions, the bosons. That's all I can say. Please. I can see so many known faces. It's a great meeting indeed. Very nice. Very nice. Amazing.
Chintan, can
Oh,
we
the
have
de
further
Broglie,
questions?
one more
Yeah.
question is, I can see them writing the question.
Yes, sir. Yes,
How
sir.
the de Broglie equation is derived, that is there, please refer to standard books. For example, refer to Halliday-Resnick, Extended Volume 2, or Sears-Zemansky. I have the book here, Sears-Zemansky. Now it is known as Sears-Zemansky University Physics, written by two other people. You will find the derivation. But friends, that reminds me, the Schrodinger equation cannot be derived as such. When you say that it is derived from something else. Schrodinger equation has to be established by basic arguments. And one of the best way to establish, to arrive, not derive, let us say, to arrive at Schrodinger equation, one of the best ways is discussed by Sears-Zemansky University Physics. There are elementary ways of deriving, not deriving, but arriving. Okay, please. A dangerous looking question. I can read it. So can I go by the questions I see on the board?
Sir. Sure.
That is a
Sure,
dangerous question and a very interesting question. Somebody is asking, the atoms and molecules are non-living. They are non-inanimate, non-living systems. What the virus is living. Virus, I don't know. It comes to the realm of biology. Virus is a link. By itself, it doesn't survive. But the question is, for example, bacteria is a living thing. So I think he is pointing out to a very fundamental question. We say that it is all made up of atoms and molecules, but merely putting down atoms and molecules does not form a life. I don't know. In fact, it's one of the fundamental questions of our existence. What exactly is life? Can the life be formed chemically? This question was discussed by Professor Narendra Bhandari in that book on meteorites, and I have translated it into Gujarati. But it is an open question. I admit I don't know. Somebody is making a comment also. Somebody is asking about the sharp boundary between classical mechanics and modern classical and quantum physics. Gradually, it's not a sharp boundary. Suddenly, at some value of the distance or some value of the energy or size, you jump into quantum mechanics. It's not like the boundary between two countries or like that. Slowly, gradually, there might be some mesoscales, they call it mesoscale systems or something. So gradually, when you talk about a large number of atoms go over to solids, it becomes classical physics. Not a sharp boundary, I would say. Not a sharp boundary. Okay. Please.
Yes, there is, sir. They are writing one more question, many questions. How come electron does not radiate energy? Even though it is accelerating in stationary orbit.
Right? That's right. That was the question raised by the people. So yes. The point is that we are trying to extend ideas of our classical physics to an unknown system. Can I say that I am going from Gujarat to some other state where they don't understand Gujarati? So if I speak in Gujarati, it is something new for them. Or I can try to extend the rules of cricket to volleyball or football. The point is that there is no reason why the same laws of physics applicable in macroscopic systems, classical systems, would hold even at the microscopic level. Therefore, we should not expect the electron to radiate. Electron is not a particle, ordinary charged particle that would radiate. It is not a particle, it is a wave, it is confined. And so confinement produces stationary states. So at first sight, it looks unreasonable. But the point is that the reasoning is not correct. We are trying to extend classical ideas. Therefore, it looks like odd. I think I've tried to explain to you.
Yes.
Please. These are standard questions. Beta emission is electron emission, although electrons are not there in the nucleus. This is a standard question. What is it that exists between the electron and the nucleus? Is it a vacuum? Yes, if you want to call it vacuum, nothing less. Or there might be some other complicated ideas where the vacuum is not a vacuum. I don't know anything about it. I say that there is nothing. That's enough. Now, what is the meaning of nothing? I leave it to you. I leave it to you because I don't know. Yes. Please see the time limit.
Yes, sir. Now I think we can. Yes. I think we can take the more extra questions from the feedback form.
Okay.
So, sir, thank you so much for this wonderful lecture.
Hello, dear.
Yes, sir.
Dear friend, I am tempted, please kindly. I am tempted to answer something. There is somebody who is talking about metastable states. Wonderful thing. This is one of the wonders of nature, metastable, which is neither stable nor unstable. What is a metastable state? For example, in n equal to 2 of hydrogen atom, we have 2s state, which is a metastable state. It means that it is not like normal excited state, which would emit energy in an nanosecond or 10 to the minus 8 second. It is prevented from de-exciting. It is prevented from immediately emitting energy and coming down to ground state. I give you an illustration. In our history, in our mythology, there was Trishanku. Trishanku was destined to be in space. He could not come down. So something like this. Now you will say, why is it that the atom in 2s state, hydrogen atom in 2s state is not emitting energy? It is prevented by the rules of quantum mechanics, traffic rules. You cannot go that way. Why you cannot go that way? Because of some conservation laws, conservation of angular momentum. This is essentially quantum mechanics, but metastable state itself is very interesting, very interesting. The whole of the idea of lasers came from metastable states. Thank you so much. It's a very nice question, of course.
Yes. Thank you so much, sir, for this wonderful. Yes,
Dr.
sir.
Forum
Yes,
is writing. Na yayatu na tatos. That's right. Yes, please. Chintan. Chintan. Hello. Please.
yes, sir. So, can we conclude it, sir?
Yes.
Yes. So, thank you so much for this wonderful session, sir. And we are very grateful that you agreed for this lecture.
My pleasure. It's my
this
pleasure.
wonderful lecture. And नन्हे से छोटे एटम की लंबी कहानी.
It is from that old filmy song. सुनो छोटी सी गुड़िया की लंबी कहानी. तो हमने बना दिया सुनो छोटे से एटम की लंबी.
Indeed, it was नन्हे से छोटे एटम की बेहतरीन कहानी, sir.
Oh, thank you. Okay, thank you. Very nice.
Thank you so much, sir. And
nice.
On behalf of all the organizers, I thank you for this lecture. I thank all the faculty and participants to join in this lecture. Thank you all.
Thank you.
And one more time tomorrow. Yes.
Audio.
Thank you, sir. Thank you.
Audio. Thank you.